before I forget. All right, so we'll be starting part 5 of this course, which is going to be about representations of Poincare group. So to just put things in perspective, I'll start by a summary of the picture so far. So in part 3, we talked about the symmetry principle, which we had this picture that we start with differentiable symmetry transformations. These were modeled by Lie groups and Lie algebra, Lie groups, and locally the tangent space would be a Lie algebra. Then Noether's theorem told us that these differentiable symmetries correspond to conserved charges, and then we saw that the conserved charges satisfy the commutation relations of the Lie algebra, right? So that was this link. All right. Then we said there are two types of symmetries. They're global. These are internal symmetries that act at every point in space-time, right? Independently. Sorry, no, not independently. They will act at every single point in space-time. And the other one are space-time transformations. So today we're going to be talking about space-time transformations. In particular, for the remainder of this course, we're going to fix the space-time to be the Minkowski space, which is RD comma 1. All right, so we're going to see that the symmetry group, what we already talked about this, is the Poincare group. And part 5 of the course is about representations of the Poincare group. And as I promised a while back, we're going to learn what a particle is. Because from the point of view of field theory, the theory is multi-particle to start with. There's no notion of a particle so far. All right, so today we're gonna study Poincare Lie algebras. We're gonna look at the projective representations of the Lorentz group. That, as we said, we need projective representations motivated by quantum mechanics. Right, one motivation to why we should care about projective representations are quantum mechanics. So Weinberg likes to say quantum Lorentz group, but that just means projective representations. We'll see that projective representations of Lorentz group will give us spinors, even though we have no central extension. So I think there was a wrong line I'd written in one of the lecture notes. I removed that, so I'll explain that completely, right? So the point here is you've probably learned somewhere in your early education in physics that there is an intrinsic property of fundamental particles called spin. From the point of view of particle physics, particles, right? Sorry, viewing everything in language of particles, not fields, spin is something that is sort of as an intrinsic property given to you. You have no way of deriving it, right? Spin is given to you. Now, here what we're learning is that if you view things in the language of field theory, spin comes out of the picture. So spin comes out of, it's forced on you because you're interested in projective representations of the Lorentz group. It's possible that you live in a universe where there are no spinors, but if you want to consider all possibilities, you're among them. And in fact, in our universe, there are plenty of spinors. And then the spin will take half integer values that we're going to see actually why. So those are observations we've made in nature. Spins are half integer, and we're gonna see why. All right. So this is where the physics, this is where all this Lie algebra and math will pay off, right? We're gonna learn something deep about nature. All right. Any questions? All right, so I'm gonna try to summarize part 4, even though it's a little bit disconnected, but I just want to make sure that we close that chapter and move on for now. We talked about gauge transformations, as redundancies that we introduced to write local action for theories with special non-local operators, namely Wilson loops. And electrodynamics is one such an example. And that's the setup where you have a Wilson loop associated with a loop like this. And there's a non-trivial observable, that's that phase that you observe here in the form of interference patterns, and it's called the Bohm-Aharonov effect. We said that there's a geometric picture for gauge theories in the language of G bundles. G bundle means that it's at every point in space-time, you just imagine some sort of imaginary internal group. That's your Lie group, right? And then your field is just some vector. If it's think of it as phi of a, some vector in this group, some element of the group. It could be expanded in terms of the elements of the Lie algebra. Lie group, sorry. It's in a representation of the group. That's what I should have said. Now, we said that if you want to define derivatives, as we usually do in physics, to write down local actions, you can't do that unless you introduce a notion of connection. This connection is a notion of a gauge field. So from the geometric perspective, gauge fields are somewhat imposed on you, right? Because you want to write down derivatives that are transforming covariantly. So a particular choice of a connection gave us a covariant derivative. This is in full generality, Lie algebra valued. And then we said field strength is really nothing but the curvature of this connection. That as you go around, so this covariant derivative allowed us to parallel transport. As you go around the loop, teeny loop, you pick up the curvature, right? And this is really the physics behind the Aharonov-Bohm effect. Then we wrote down gauge invariant action in terms of the field strength squared, right? We explained this action, where it comes from, Yang-Mills action, right? And then we said Wilson loops are non-local observables, and they can be zero even if F mu nu is zero everywhere along the curve, right? This was the example of Bohm-Aharonov. Now, to come to the question that was asked earlier, there are other non-local observables if there are charged particles. So if you have a charged particle, two charged particles, you connect them by a Wilson line, and if this guy transforms in an anti-fundamental and this guy in a fundamental representation, then the result is gauge invariant. Why? Well, this is how the fundamental one transforms by some u. I should have called it R, sorry. This is the anti-fundamental, and this is how the Wilson line transforms. You see the cancellations, right? And you end up with something that is gauge invariant. So what we learn is that if you have charged particles in a gauge theory, they should always be dressed using Wilson lines, right? So if you can think of it as like a quark anti-quark, or as an electron, quark anti-quark, and they're attached by some sort of a Wilson line. As you try to separate them, you might feel a force, positive or negative, and that could be attributed just intuitively to the tension of this quote-unquote string Wilson line that attaches them. So there's a deep, old story about how you could view these. Anyway, so there's a huge literature on this, because as we described, gauge theories are everywhere in physics, right? They're very important. Then finally, we said that gauge theories are natural from the point of view of lattice theories. Every time you put degrees of freedom on links, in particular, if you put a Lie group representation as a degree of freedom on a link, and consider this particular Hamiltonian, right? You end up with in the naive continuum limit, you get the, in the naive continuum limit, you get the Yang-Mills action. So there was a question on Slack, why this Hamiltonian? Because it's natural and it has the symmetry, right? We're not saying that every Hamiltonian you write down will have once you put degrees of freedom on the links, will have symmetry of this type. But so yeah, okay. There's a little bit of a longer. There's a bigger philosophy behind this, but we will not get into that. So this was a summary of section 4, part 4. We're gonna close this chapter for now. Move on with our exploration of space-time symmetries. These are honest-to-goodness symmetries, and in particular in flat space with the Poincare group. Any questions about gauge theories before we close out? All right. So Poincare group. Poincare group is we're talking about space-time transformation. Let's flat space. Let's say I use coordinates x mu, and there I make a coordinate transformation of this form, diffeomorphism, a continuous transformation, and the metric is eta mu nu. It will give me the proper distance, and the symmetries of flat space are coordinate transformations that leave the metric invariant, which means that they leave the proper distance invariant, right? The proper distance between me and another friend of mine in Andromeda Galaxy, I don't know how we met, is invariant under Poincare transformations, right? So it's not hard to see that the set of such transformations are basically could be written in this form, where these are, these are translations, right? And these are the Lorentz transformations. So for a matrix like this, a tensor like this, to be to leave the metric invariant, you should have this Lorentz condition, right? And we already talked about what these matrices look like. We're going to come back to it. But one obvious thing is that the determinant of lambda squared has to be 1, which tells you that the determinant of lambda is plus or minus 1. The group that satisfies these relations is called OD, 1. These are orthogonal matrices that preserve the metric that has d1s in the space direction and a -1 in the time direction, right? And we usually write the Poincare. So this is your Lorentz group. It's a group. Sorry, I shouldn't say disconnected. It's a group that's not connected, right? And we usually write it in this way. I just want to write down in this form, if in case you see it, and don't freak out. This is mathematicians. If you know what the semi-product is, that's what this is. It's a particular way of combining these two groups, but it doesn't matter. This is what the group is. Think of it as the group generated by Lorentz transformations and translations. All right. Sometimes the Poincare group is called the inhomogeneous Lorentz group. I'll try to avoid that terminology. So as I just said, you could label the Poincare transformations using the boost, sorry, not boost, Lorentz transformation lambda and translation A. And it's easy to check that this is a group, as a group, the inverse of this transformation is written in this form, where you just take the inverse of the Lorentz transformation and the translation will change accordingly. All right, so this is the group we're going to be dealing with. Today, we're going to mostly talk about this part, the Lorentz group. That's a complicated part, because this part, the translations, is commutative. It's a commutative algebra. It's a very simple group. Any questions? So I have to tell you that as we go through this, there will be some abstraction happening. And it will pay off. I promise you it will pay off. And I told you in advance, it will tell you what a spinner is. Spinner, the notion of a spin will come out of this constructing the representation theory of the Lorentz group. That's why we're going through this. So as physicists, at least I operate under the principle of minimal effort. I learned the minimum amount of math that I have to learn to describe the physics around it. I'm not aware of a way of explaining spin from a point of view of fundamental physics without going through this representation theory. If there is a way, I would love to learn it, and we'll replace this lecture with that. All right, so the Lorentz group. The Lorentz group has a very important discrete subgroup that you have already learned in physics about. Parity, this is a transformation that leaves time invariant, but flips all the spatial directions, something you've learned in quantum mechanics, and time reversal, where you only keep the space fixed, only flip the time. So we usually call this P and this T. So PT, applying both, corresponds to the minus the identity matrix. Good. Now, immediately you learn something here. Minus the identity matrix might have the determinant of minus the identity matrix is either 1 or -1, depending on your space-time dimension. That is where actually this is one of the origins of why the representation theory of Lorentz group is different in even and odd dimensions. Okay, so you might have heard about symmetries of quantum field theory being CPT, charge parity conjugation. We won't get there today, but by the end of this lecture, you're going to see some hints at why we need a charge, a notion of a charge invariance. But there's also another thing that's often said. There's a way of formulating all of this, which is dimension independent. There's a symmetry called CRT. That's a symmetry, that's an honest to goodness symmetry of quantum field theory in every dimension. But let's not talk about that. If you guys are curious, I'm happy to tell you about it. But from now on, well, I'm just going to make a comment about even and odd dimensions. And from now on, after this comment, we're going to forget about odd dimensions, stick to 3 + 1 dimensions, because that's a dimension of dimensionality of space-time. We're going to be working with that. But for now, in every even dimensional space-time, you can start with a set of Lorentz transformations that have determinant 1 and lambda 0, 0 larger or equal to 1. Right? So hopefully it's clear that this part of the Lorentz transformation is continuously connected to identity. Right? Because identity has lambda 0, 0, 1. And it has determinant 1. You apply a parity, your lambda 0, 0 hasn't changed, but your determinant changes. This is a once you apply parity, you go to another piece of the Lorentz group that you couldn't reach continuously, because no continuous transformation can change the determinant from 1 to -1. Right? So these are disconnected. You apply a time reversal transformation that brings lambda back, determinant lambda back to 1, but it flips, it takes lambda 0, 0 to less equal to -1. Now, this is not connected to identity. Again, we haven't come back where we were. You have to apply another P so that you come to delta lambda -1 and this guy, and then you apply another T, you come back where you were. So you end up in even dimensions, you end up with 4 disconnected components in the Lorentz group. And you go in between them using parity and time reversals. So remember, here's an important notion. We talked about Lie groups and Lie algebras as being the local tangent. If your Lie group has disconnected pieces, by moving along the tangent vector, there's no way you can get from one to the other one. So you could have 2 Lie groups that are locally identical, because the tangents are the same, but they're globally different. And that has to do with the number, whether or not they're connected, or actually more than that, whether or not they're simply connected. So we're going to work towards that. I don't want to bombard you guys with group theory, but the simple connected notion is important. All right. So you have so basically in short, in space-time dimensions that are even, you have 4 disconnected components that have to do with the determinant of metric of Lorentz transformation being positive or -1, and whether the 0, 0 component of the transformation is larger or equal to 1. And in odd dimensions, you only have 2 components. The reason is that parity does not change the sign of this guy. If you apply parity transformation in odd space-time dimensions, the sign doesn't change. Right? Because in odd space-time dimensions, you have an even number of space dimensions. As you multiply by minus sign, nothing changes. Good. Any questions about this? So this is where we're just discussing the global part of the story. Now we're going to come back to the local bit for a bit, the local part in a second. All right. Now, because it's, if you recall, when we were discussing Lie algebras and Lie group, we looked at the Lie group and sat near identity. So because of that, we're going to focus on the component of the Lorentz group, which is continuously connected to identity. That is called restricted Lorentz group. It's written as SO plus D comma 1, or sometimes called this funky word, proper orthochronous Lorentz group. I'm just going to call it restricted Lorentz group and write SO plus D comma 1. So is that good? So that means this bit. That means this part. If you want to know what's going on with the other parts, just apply P and T. Right? P and T's are the score to identity. Okay. They might or might not be a symmetry of your theory. This is important. This is very important. Time reversal or parity might or might not be a symmetry of your theory. Well, we'll get there. We'll get there. Okay. Very good. So now this thing, SO plus decon 1 restricted Lorentz group, is connected. It's a connected Lie group, but it's not simply connected. So you're going to work out, well, okay, just to tell you what it is, connected, you know what connected means. Disconnected, an example of a manifold that's connected but not disconnected is this manifold. Simple connected means that every loop could be shrunk to a point. So for example, sphere is simply connected because every loop could be shrunk to a point. Importantly, the group that we care a lot about is the rotation group. And rotation groups, SON, for n larger or equal to 2, is not simply connected. This is the origin of spinors. This is literally the origin of spinors. The fact that SON is connected but not simply connected. So you're going to work out to in your homework why SO3 is not simply connected and how you could make it sit inside the larger group called SU2, you already recognize, which is nothing but a double cover of this. SU2 will be connected. So I'll give you a picture of what's going on. But this mathematics I'm going over is essential because it's going to explain to you what spinors are. This part was quick. We're going to come back to this, okay? So I just wanted you guys to remember this thing that SO3 or SON comma 1 is not simply connected. Just remember that. You don't even need to remember what simple connected means. All right. We said that fields transform in some representation of the Poincare group. All right, so it means this. It means that there will be some S of lambda of A as a matrix that acts on the field. And it's a representation, so they should multiply like this. The multiplication, matrix multiplication should be representation multiplication. If we are talking about representations, we might be talking about projective representation if we were talking about the Hilbert space. At this point, I'm just doing abstract discussion. All right. Is it all good so far? I think this comment belonged to earlier in an earlier slide. All right. Now that we focus on the Lorentz group, the restricted Lorentz group, let's look at this Lie algebra. So an infinitesimal Lorentz transformation, you could expand them near identity because this is the restricted part. And you get with these W mu news. And we discussed this in earlier when we were discussing special relativity, that this is anti-symmetric. This is anti-symmetric. And then A mu, infinitesimal translations are just some epsilon mu vector. All right. This is a D plus 1 times D plus 1 anti-symmetric real matrix. How many degrees of freedom does it have? D times D plus 1 over 2. These translations have D plus 1 degrees of freedom, or generators of the Lie algebra. So in total, you have this number of generators. So let's do the math. In 3 plus 1 dimensional space-time, you have 6 degrees associated to Lorentz transformations. 3 of them are boosts, 3 of them are rotations. So that checks out. You have 4 translations. You have a total of 10 parameters in your Poincare group. Once you take this S matrix representation matrix and expand it, it's conventional to put these factors of I omega mu nu, or I over there, and half. These are the 6 generators of the Lorentz transformations, and these are the 4 generators of translation. They're called momenta. You already know those. In a unitary representation, these guys, from Wigner's theorem, it follows that these guys better be Hermitian. So momentum is a Hermitian operator. That's the origin. Because Wigner's theorem is the origin. So in your homework, you will derive the following thing. So if you recall, when we talked about Lie groups and Lie algebras, we took a Lie group, expanded it near identity, and imposed a bunch of group multiplication relations and derived the Lie algebra as commutation relations of generators. In your homework, you're going to do that and discover or derive the Lie algebra of the Poincare group. Poincare Lie algebra, sorry. This is the Poincare Lie algebra. Of course, translations commute. Translations and Lorentz transformations do not commute. And of course, Lorentz transformations among themselves did not commute. Any questions? All right. So it's a good moment to instantly talk because these are symmetries. Let's remember Noether's theorem. Noether's first theorem told you that if you have a Lie group of symmetries, differentiable symmetries, you have conserved charges. So what are the name of these conserved charges? I already said that. P0 is Hamiltonian. Pi are the momenta. J0i is our Ki, their boosts, and Jij's with this epsilon ijk. With a minus sign, you could turn them into the standard Jk of angular momenta. Right? That's the counting in 3 plus 1 dimensions. So the symmetries, you recognize all of them. Now, if you remember also from our discussion of symmetries, we said that conserved charges that you construct from Noether's first theorem, they satisfy the Lie algebra commutators. Here they are. I just expanded them. They satisfy the same Lie algebra, right? This part of the algebra that I'm going to be focused on is the Lorentz subalgebra, because it's only written in terms of the angular momenta, boost. Yeah, angular momenta and boost. All right. Is it all good so far? Now I'm going to play a trick. The trick, I'm just going to present it as a trick, as it's presented in a lot of textbooks on quantum field theory, but we're going to come back and say a few words about the representation theory origin of it. In 3 plus 1 dimensions, you could do a smart rewriting of, of the Poincare algebra. The Lorentz algebra. The Lorentz algebra, this guy. What do? You define Ji plus minus I Ki. I is the square root of -1. So you get 2 generators, Ni plus minus. If you just write down the commutation relation in these new variables, you find 2 copies of SU2. It will be consistent with my notation. 2 copies of SU2 Lie algebra. 2 copies because they commute among themselves. So what did we learn? We learned that the Lie algebra of Lorentz transformations could sit inside SU2 cross SU2. When I say sit inside, is because this operation of plus minus 1i is called complexification in math. So if you want to write an identity, you put some complexification, you write this down. But we're not mathematicians here, so we don't care about that. We just write it this way. All right, good. So what did I do? I rewrote the Lorentz algebra, the generators of the restricted part of the Lorentz algebra, in terms of 2 copies of SU2 by rewriting of my degrees of freedom to SU2 Lie algebra. The fact that the Lie algebras match don't mean that the groups match. Recall? This was important. And that will be the origin of spinors. That is the origin of spinors. All right. Any questions so far?
By SL31, do you mean the special linear group? It's Lie algebra.
Oh, I'm so sorry. Sorry. Thank you so much. What? Thanks for the correction. SO3,1. Why did I write SL3,1? Sorry, SO3,1. That was a terrible typo. Sorry about that. Thanks. So just the Lorentz Lie algebra. Thank you for the correction. Sometimes these typos are, I don't even see them. Usually definition typo or something like this. Anyway, any other questions? Thanks for the correction. All right. Now, here is where the spinors come from. The spinors come out of the fact that you want projective representations next to regular representations. So let's pause for a second. I'm going to tell you a story that they could have taught you in quantum mechanics. Forget about field theory. They could have explained this to you in quantum mechanics. And actually, when I was going over earlier, when we were working out the example of Lie algebra of SO3, this question came up. I wrote everything in terms of SU2. Then I wrote down the representations of SU2, and you found integer and half integer representations. So integer representations of SU2 map to integer representations of SO3, but the half integer ones are spinors. They're not viewed as the representations of SO3. They are actually projective representations. So we're going to go through that. So this story of spinors, you could have discovered them in quantum mechanics as well. You didn't really need some of this fancy stuff, right? Oh, all right. So we're going to be talking about the representation theory of the restricted Lorentz group, SO, we call it plus? Yeah, SO plus D comma 1. This depends on the dimension. As I said earlier, we focused on 3 plus 1 dimension. Now I'll give you as a homework the 2 plus 1 dimension, which is an easier case. This Lie group has no, oh, what? Sorry. What have I written? I wrote the same thing that I had written before that was incorrect. So, oh, sorry, no, that was correct. That was correct. A Lie group has no projective representations if 2 properties are met. First, it has no central extension. Second is simply connected. So this is something that I glossed over. I didn't really explain much, and I just pointed you to Weinberg's book for this. But now I'm explaining it. I'm saying it. So SO plus D comma 1 has no central extension. We said that, right? Because central extension meant shifting the right-hand side of the commutator by identity. But SOD comma 1 doesn't have identity in the generators, right? Because all the generators are traceless. So it doesn't have Lie central extension, but it still has projective representations known as spinors because it's not simply connected. That's where spinors come from. There's no central extension, but there is the manifold is not simple. All right, let's explain this simple connected business a little bit more. We're going to use a notion called covering. Covering is a very geometric thing. Let me give you an example. R, not R plus, R, a line, real line, is a cover of S1 because you could view it, you could wrap the line like this, and you could view it as a stack of pancakes over the other manifold. Now, the point is that SU2 is the double cover of SO3. So SU2 could be viewed as a double cover of SO3. You do SO3, come back, you do 360 rotations or something, come back, you do it again, and now you identify the final point with the initial points, you get SU2. It's a double cover. You're going to work that out in a homework. But it's a double cover, but locally, the Lie algebras are the same. They're identical. So SU2 Lie algebra, this is my attempt to write a different notation for Lie algebras and Lie group. These guys are the same. If you want to identify their generators, if these are the generators, angular momentum generators, just identify them as 1 over 2i, sigma I. Sigma I are the Pauli matrices. This is identification. But I repeat, Lie algebras match, but globally, the two manifolds are not different. One of them is a double cover. SO3 rotation group is not simply connected, but the double cover of it is often called spin 3, otherwise known as SU2, is simply connected. Therefore, the double cover of it, SU2, has no projective representations. This gives you this nice picture that representations of SU2 give you produce for you projective and regular representations of SU3. So we went through this in the example without explaining it. The representation theory of SU2 will give you integer spin, which would correspond to regular representations of SO3, and half integer spin, which correspond to projective representations of SO3. We're not teaching Lie groups here, but the grand picture is that the projective representations of a Lie group can always be extended to an ordinary representation of its universal covering group. If that doesn't say much, forget about it. The point is that you're dealing with SOD, 1 plus. This is the restricted Lorentz group. The universal cover of it is called spin plus D, 1. This is a connected and a simple connected manifold. It's a double cover over SOD plus 1. D, 1. So all of this math, if you want to forget about all of it, it's perfectly fine. Just remember that the way you construct regular and projective representation of the Lorentz group is through some mathematical framework by finding and classifying all representations of S pin D, 1 plus is some other group, which is simple connected. It's a universal cover. It's a double cover. You just go around it twice. This going around twice won't make sense until you work out that homework problem that you see that SU2 is a double cover of SO3. All right, this was pretty quick and a lot of math. Any questions? Are there any questions? I think I went through this pretty fast. So it's a good moment to pause. Right? Let me try to summarize. Maybe as I summarize, things will come up. We started by looking at space-time transformations that were symmetries of flat space-time. These guys were Poincare group. There were two parts of the story. Translation that generate there an abelian group, abelian algebra is RD, 1. And the Lorentz transformations, there were OD, 1. Now, we said in even dimensions that we were focused on, 3 plus 1 dimensions, there are four components that are disconnected, and you could go in between them using parity and time reversal. We focus on the connected piece around the identity. We call that the restricted Lorentz transformation. Every time I write SO3, 1 plus, that's the restricted Lorentz transformation. This is a Lorentz transformation that are continuously connected to the identity. Our goal is to construct a representation theory of this and classify the finite dimensional regular and projective representations. Mathematically, you do this by constructing a double cover called a spin plus 3, 1. Sorry, d, 1. And by classifying all the regular representations of that, because that thing doesn't have any projective representation, you get a handle on all the projective and regular representations. All right, so what is this spin 3 plus, 1? This is SL2, C. It's a group. There is, if you started with spin 4, that's SU2 cross SU2, 2 copies of SU2. At the level of the algebra, this SO plus 3, 1 could be mapped into 2 copies of SU2, left and right. This is precisely the map that I wrote down earlier. These were the transformations, the generators of the SO3 plus, 1, right? Boost and rotations. I wrote them in terms of these generators, and here are the 2 copies of SU2 for me, left and right. So if I want to understand all the representations, regular finite dimensional EREPs of finite dimensional, representations and projective representations of the Lorentz group, I just need to look at regular representations of SU2 left times SU2 right. But you already know that from basic quantum mechanics. It's just it's labeled by 2 spin variables, J left and J right, that take half integer values. Good? So here's where we're going to claim success. This basically gives us a grand understanding of all the EREPs, finite dimensional EREPs, of the Lorentz group in 3 plus 1 dimension, projective and regular representation. These are the things that are going to become particles for us. This is the punchline of this section is that these are all the particles that we're going to have ever in 3 plus 1 dimensional space-time, flat space, in quantum field theory. These are all the things that we have available to build our theories with. All right. Any questions here?
Yeah, these J's we have here though they're no longer just corresponding to rotations though, right? Because we have the J and the K's are mixed up in these ends, right?
Yes, absolutely. They're somewhat, yeah, they're mixed up. They're mixed up. Yes. That's right.
Another question.
Yes.
Why do you call them left and right? SE2 left and SE2 right? Is that terminology or some like?
No, it's not terminology. Well, it is terminology, but it has to do with, well, okay, we're gonna get to that stuff. Chirality. It has to do with the notion of chirality, left chirality and right chirality. Okay. Well, at a deep level, yes, it's convention, left and right. Fundamentally, you could call this plus and minus, yes, but these are related to chirality. So, any other questions? So I repeat, these are all the particles I can ever have. Well, I haven't told you that these are particles, but these are basically all the particles. So now let's look at all the representations we constructed and enumerate them. It's easy to organize fields in terms of these EREPs of SU2s. So I'm just going to get these labels of J left, J right in terms of the EREPs. And now I remember I can organize these such that the representation of the G left acts on the left this way, and the representation of right acts on the right this way. It's very familiar from mathematics, group theory, but if you wish, that's one way of talking about left and right, why they are left and right.
So when you write it like this, it's a convention that the left one acts on the left, right one acts on the right, or?
So you see, this is, no, it is a choice of, yeah, this acts on the left, this acts on the right. Yes, it's convention. It's just notation. Okay. At this point, it's notation. That's all. Okay. But what's important here is that this field transforms under Poincare Lorentz transformations in a representation, irreducible representation that has dimension 2j left plus 1 times 2j right plus 1. So let me try to demystify this. It's actually, it takes a lot of getting used to understand the physics of left and right, these guys. So let's just list all of these because there are so many options. If I pick the representation left and right, both of them to be the singlet representation, I'm going to use the symbol phi for it. There is 1 degree of freedom because this representation is one-dimensional. This is a scalar field theory. This is a scalar field. We found it in nature, Higgs particle. You could have representation half for left movers and 0 for right movers. We usually use this notation chi alpha, and I apologize already for this notation, but it's very, very standard. It's a two-dimensional vector. It's a two-dimensional, it has 2 degrees of freedom, let me call it that way. This is called a left-handed Weil spinner. You could have 0, 2. We usually write it as chi bar alpha dot. Alpha dot is a parameter. It's like alpha that runs from 1 and 2, but people call it alpha. Use the notation alpha dot. It's very bizarre. I apologize. This is the notation. And the reason for bar will become clear in a second. Well, I might not get to explain the origin of it completely in this lecture, but I'll make a comment about it. These are the right-handed Weil spinners, and there are 2 degrees of freedom. Now, the Poincare one is half-half. This is a 4-dimensional representation that carries 2 indices. This is actually a Lorentz vector. This is a Lorentz vector. It's hard to see, but it takes some sort of work. Spinners are not supposed to be intuitive. Let me just say it right away. Spinners are not supposed to be intuitive. You saw that I did some sort of funky transformation. I added boost. I mixed rotations and boost by some I, and I did some funky transformation to generate these groups and sort of decouple these 2 left and right movers, right? So don't expect this to be intuitive. Intuition only comes from working out many, many examples. All right. Each Weil spinner, left movers and right movers, they have 2 components, so we could view them this way. And the transformations under Poincare transformations are standard good old SU2 representations of the Pauli matrices. All right, now let's focus on this Lorentz vector. If you want to go in between the standard Lorentz vector, V mu, and this funny way of writing the Lorentz vector, there is a way to write them in terms of each other by just working out the representation theory. And this is what sits in the middle. These are Pauli matrices organized this way. Now, what is important to remember is that this guy does not transform under Lorentz transformation. This is just a set of numbers. The thing that transforms nicely is this guy. This is just a set of numbers. There's really nothing here. I just told you, this is the proper EREPS, the left side. I just wrote about how to go between this basis and some other thing. Now, what our group is, so here recall that my group was the group that I was hoping to classify the representation of is the universal cover of spin 3,1, which is, sorry, is the universal cover of the restricted Lorentz group, which is SL2C. But I didn't do that. I looked at the Lie algebra, which was SU2, SU2, and I looked at the representation theory of this. But these 2 groups also are very different. There is one important difference between them that has physical consequences. When you talk about SU2, SU2, the left and right movers are completely uncorrelated. They are not related to each other. They're completely independent. But in SL2, C, the left and right Weil spinners are not independent. Right. Yeah. They're not independent. As a matter of fact, they're complex conjugates of each other. So I haven't explained this to you guys. This is not something that you see unless you work out in detail a lot of examples, but they're complex conjugate of each other, hence this funky notation of bar up here. There is, this is very fast, quick, but I want to make another comment here. In OD plus 1 parity transformation, swaps SU2s left and right. You just have to write these down. At least I do not have any intuition for these things until I spell out how the transformations act. So your homework are going to be a lot of these transformations. But in OD comma 1 parity, what it does is that it sends the left movers to the complex conjugate of the right movers. That is part of the origin of these. Importantly, parity need not be a symmetry of the action you write down for spinners. This is very important. You could build a theory purely out of left moving while fermions. Now, okay, this is important. Let me say this. I'm going to pause and discuss some physics because I went over a lot of math here. We're going to see in the next lecture that if you take a right moving while fermion and apply a 360 rotation to it, it doesn't come back where it was. It'll pick up a minus sign. It's a projective representation. Could such a thing be observed in nature? Can you ever see can an observable must be Lorentz invariant in a sense, right? You should rotation invariant. Like if you go 360 around, sorry, not Lorentz invariant. If you go 360 around, it should come back to where you started. It was a property of this projective representations. We discussed them because they were natural in the Hilbert space. Here we're discussing them just abstractly, right? Because we can, and it turns out that they are realized in nature. Now, if my spinner field is such that I go around 360 degrees, I take my spinner, go around and come back, and it picks up a minus sign, could such a thing be observable? No, it means that spinners are never observables. What are observables are bispinners. If you have two spinners, now that thing is fine. Because if you take that thing and anyway, we'll get to this, right? But spinners, as opposed to scalar fields are observables, right? So you could observe them, but spinners are not. You always have to have even functions of them so that they are observable. We're going to go over these. I know that usually in every course in quantum field theory, spinners are the most painful part because they're very counterintuitive and they're ugly to work with. But if you want to really understand nature is full of spinners. We have a lot of spinners, right? And you have to work with this. It helps if you know more group theory. That's why I'm walking you guys through this group theory. Without group theory, all of this seems like full of insane magic. All right, so now let's talk about these wild spinner algebra, these modes. If you take two, now I'm doing this because eventually I'm going to write down an action for these spinners only. If I take two spin half EREPs and put them together and anti-symmetrize them, as you probably remember from your quantum mechanics, you get a singlet. This is a spin 0 EREP, and you could write it as introducing an epsilon tensor in this 2x2 representation as epsilon alpha beta, psi beta, chi alpha. I'm working only with left movers, left while spinners. This is a Lorentz scalar. This is sometimes called the spinner metric. Don't try to read too much into it. Okay, so now the reason it's called spinner metric is that I can use this epsilon tensor thing to raise epsilon spinor metric to raise and lower indices. And this guy is a scalar in this notation. Now, one thing to be careful with is that this notation could be very misleading. In particular, psi alpha chi alpha is not equal to the lower ones. Think about that. Because it's not a metric, it's something else. Now, we said that here's an opportunity to say one more thing that you might have heard about spinors, that they're Grassmannian. Take this psi alpha, and I said it has two components, psi 1 and psi 2, right? So let's just say I don't realize that this is in a two-dimensional representation, and I'm just gonna look at my view these guys as independent degrees of freedom, as if they're independent degrees of freedom, and look at my Lorentz scalar. It's psi 1, psi 2 minus psi 2, psi 1. If these were just like ordinary commuting things, this would vanish. But they don't. In fact, these guys, if I want to view them outside of the framework of vectors and representations, these are anti-commuting. So psi 1, psi 2 plus psi 2, psi 1 is 0. This is the origin. Actually, psi 1 squared is 0, psi 2 squared is 0. This is the origin of this anti-commutation relations and Grassmannian picture. But if you view it in terms of representations and two-dimensional vectors, and this guy, this epsilon thing, you're never going to get confused. All right. Any questions? Let me try to summarize. So what did we do? We said we're interested in studying the, hopefully by now you realize that why I'm using this whole, I'm devoting a whole section of the course to discussing the representation theory of Poincare, because it's involved. So we want to construct field theory and look at symmetries in flat space, in Minkowski space. These are the symmetry transformations that preserve the metric of the flat space, which is -1, 1, 1, 1. In 3 plus 1 dimensions, let's stick to that case. We said that this symmetry group is a Lie group. It has a part that's translation. It has a part that is Lorentz transformations, which is O3, 1. Right? This is the orthogonal group of orthogonal matrices that preserve the metric with 3 pluses and 1 minus. Keep that metric reserved, otherwise known as eta. Okay. Then we said that there are 4 different disconnected components in 3 plus 1 dimensions, and I can go in between them with parity and time. Then I focus on the component that is connected continuously to identity. That was the restricted Lorentz transformation. We wanted to construct a representation theory of this. Now, because it's a semi-simple group, because it's this guy doesn't have an identity in it, in this Lie algebra, it cannot be centrally extended. But because it's not simply connected, it could have projective representations. And we saw that the projective representations have to do with spinors. Then we switched gears and used Lie algebras and Lie groups to classify all possible representations and projective representations, finite dimensional, that's the caveat, of this SO3, 1 plus. The way we did it was by considering a universal cover. It's called SO3 plus spin 3 plus 1 spin 3, 1 plus. That is maybe complicated, but locally simple. Globally is complicated. It's actually not globally complicated. The globally, it doesn't have any, it's a semi-simple group, so it doesn't have any projective representations. It's all, we classify all as regular representation. It's actually a little bit involved. It's SL2C. It's locally 2 copies of SU2. So we use these 2 copies of SU2 to build representations, regular and projective, for our restricted Lorentz group. We discovered that, of course, because these are two copies of SU2, they're going to be labeled by two variables, J left and J right. These are spins for left and right modes. Now this is all that there is to feel all the matter content, matter content we can write down in field theories. I'll explain that in the next few lectures. But we saw that if you pick the representation, which is 0, 0 of both of them, this is a single representation of both of SU2s. This is a scalar field. This is a good old scalar field. The representation half 0, half comma 0, and 0 comma half, these are Weil spinners. Weil spinners, they are projective representations. You would have never discovered these if you were focused on representations alone. If you don't care about all this covering, universal covering group and such, just consider it this way. I gave you a list of all the possible representation, and I had some magic to discover all of these. So there are these are Weil spinners. We're going to see later that one of the beauties of field theory is that you're going to learn that spin is tied to statistics. That's going to be very, I guess, it's a spin statistics theorem. If you have a spin of the particle, well, I haven't told you it's a particle yet, but we'll decide it's statistics, but we'll get there. Then we said that the half comma half is the good old vector field. Does anyone know what, which one do I want to ask actually? 1 comma 0 is? So there are other representations you could have. You could have, right? Think about these actually. 1 comma 0, 0 comma 1. You have two of them, left and right. And you have 1 and half, half and 1, and you have 1 comma 1. Importantly, I didn't write anything beyond 1 comma 1. There's a reason for that. But we'll get to that. We might or might not get to that in this course. If you require quantum mechanics, you put quantum mechanics next to relativity. We haven't discussed quantum mechanics yet. So far, I can write whatever half integers I want. I can write 17 over 2 and 32 over 2. 33 over 2, right? But once you introduce quantum mechanics, it tells you that, well, this is all you've got next to those other ones that have. The other ones cannot be consistent. So spin, it will actually tell you a bunch of things. So now, in anticipation for, I don't know whether we're going to get there, but it will tell you that the theory will have, no particle can have spin larger than 2. Total spin. The spin 2 particle is unique. It's graviton. And then the spin 1, spin 3 halves, spin 3 half is gravitino, or like spin half, or all sorts of things. But that's all that there is. There are no other things. This is it. This is kind of like magically Lorentz symmetry is very, very restrictive. So this philosophy is, look, again, I want to emphasize it's locality that's doing this magic. Quantum mechanics would have told you that you could write anything pretty much, right? But now you're requiring a local action that transforms nicely or is invariant under Lorentz transformation. That is extremely restricted to the point that it tells you that the types of particles you can have, there will be some notion called spin. The spin is fixed. It takes very, very fixed values, and that's all you've got. This is all you've got you can work with. There's nothing else. We haven't described the quantum mechanics side of it. Quantum mechanics also, unitarity is a very strong constraint. All right. Any questions?
How is this epsilon alpha beta that is phi beta chi alpha thing a Lorentz scalar?
Sorry, how is this a Lorentz scalar?
Yes, that one.
This is the when you have two spin half particles, right? Let's say in quantization of the hydrogen atom, 2 electrons, right? you could put them in the up, down, minus, down, up as a same way.
Okay. So you basically wrote this from an analogy of that, like from.
It's not an
I thought.
analogy. It's this that spin half, tensor spin half could be split into 0 plus 1.
Okay. That's how you wrote it.
The same
Okay.
sort of Clebsch-Gordon coefficients. It's the exact same story.
Okay. Because I
about the
couldn't
theory of
immediately see how
multiple
this followed
particles.
from the
Right.
discussion.
That's the theory of multi-particles. I haven't described that yet. I haven't even told you that these are particles to talk about multiple particles. But yeah. All right. We will see. And so continuing with this theme, and we're in part 5. So we started part 5. You should be a little bit confused because I threw a lot of concept math at you. But the next 2 lectures, the goal of them, the same way the whole, usually the first lecture, every part is somewhat confusing. Hopefully the next 2 lectures are going to help understand some of these concepts, get a better grasp of them. And the punchline is going to come in lecture 12, where we say, what is the physics behind all of these representations? The punchline, I've told you this before, every irreducible representation is going to be a fundamental particle. So it will give you some sort of principle for like building blocks of what the theory, what kind of matter you could have in nature, right? Yeah, that will be the punchline. The spinner, I should tell you this, that this section of the course particularly is calculational heavy because it involves some heavy, if you haven't done group theory, it will involve some sort of index management. You should be organized with manage a lot of indices. All right. This is the end of this lecture. Are there any questions?
You mentioned that SL2C locally looks like 2 copies of SU2, right?
Yeah.
And we are trying to find out all the irreducible representations of SL2C. What we did is to look at those representations of SU2 cross SU2. And
Yes.
why can we do that to find out the
You're saying that why I didn't directly construct a representation of SL2C for you?
Yeah.
Well, what I did is just, if you try to do that, mathematicians have learned the way to do it is to go from SL2C to 2 copies of SU2. There's a method for that. There's a method to that. It's complexification. And there's a path that basically takes you along all the representations of SL2C, representation of SO3, 1, all of that is understood in terms of the representation theory of 2 copies of SU2. So I'm not teaching Lie algebra theory here, Lie group theory here, but if you want to do that, there's a full theory of Lie groups. And if you want to systematically study this, you go to SU2 across SU2 and just come down. So I just told you the final result, and I was just hiding a lot of subtleties. I do recommend skimming through the Wikipedia article on representation theory of Lorentz group. It will help. You will read some statements besides this text, besides what I'm telling you, which you might find helpful, because it goes through a little bit of history behind it and how these representations were discovered. There are a whole bunch of infinite dimensional representations. I'm not discussing them here in this course, but yeah.
All right, thank you.
Sure.
So do we see the like the complex conjugating taking us between L and R? Is that just because of the way we decoupled it into 2 SU2s? Like doing a conjugation flips the sign of the J plus IK, and that flips us from left to right.
Yeah, there's a way of actually seeing how SO3, 1 sits inside 2 copies of SU2, and you try to keep track of. So sorry, maybe my comment was a little bit confusing, but the point is that SO3, 1 sits inside 2 copies of SU2. Now you want to focus on those transformations that were originally inside SO3, 1 and get rid of the other ones. Right? So this might end up with too many, like, I don't want to say variables because number of variables is the same, but one of them is larger, One of them is larger, right? So you have constraints to impose. Coming down to SO3, you have constraints to impose. I'll try to explain that a little bit more. But for that, well, I mean, we have a whole lecture on spinors. If you weren't satisfied by the end of the next lecture, ask me. Any other questions? By the way, in full honesty, I have to say this. Every time in my whole career, I had to do a calculation that involved spinors. I bring all my textbooks, put them in front of me, because notation is horrendous. And you need to make sure that you get everything right. So just know in advance that working with spinors is going to be a little bit more calculation heavy and index heavy and less intuitive, at least for me. Maybe there's someone out there who understands spinors in a very intuitive way. I do not. But, yeah. Group theory is a way to save time. If you want to do these calculations efficiently, you do group theory. You learn group theory. That's what you do. All right. Any last question?
Is there an easy way to see that the components of this spinor are anti-commuting, or is that something we'll talk about later?
I will not talk about it because that was just a side comment at this point. If you view them as vectors, there's nothing to worry about, right? The representation picture as a vector space is very clear, right? That becomes important when you want to view the theory in the language of path integrals. So when you want to use path integral formalism, then commutation versus anti-commutation and those things, you want to somehow use Grassmanni variables versus not. But I will not have more comments on this. Maybe, I don't know. As I write the next lecture, maybe I find a good opportunity, but I doubt it. All right. Okay, thank you so much, guys. Let me just say one more thing before I go. There was one line in the previous lecture notes that I removed already on the updated version. I had written something that was incorrect. So let me just say it again to make sure we get the everything clean. Poincare group has no central extension. However, it has projective representations, and those are spins. I had written somewhere that it has no projective representation. That's wrong. Okay, just like incorrect. All right. It has to do with the fact that it's not semi-simple. That's all. All right. Thank you so much, guys.
Okay.
Have a nice day.